A queue is a linear data structure that follows the first-in, first-out principle. The element that arrives first is the first one to leave. Think of a line of people waiting for a ticket counter. The person who joins the line first gets served first. The basic operations are: in QX, add element X to the rear tail of the queue. DQ, remove and return the element at the front head. Front or peek, look at the front element without removing it. Is empty true if no elements are stored? Is full true when the implementation cannot accept more elements relevant for fixed size arrays? Properties. First in, first out order guarantees predictable service order. All operations, when implemented correctly, take constant time big O of 1. The queue can be bounded fixed capacity or unbounded dynamic growth. A linear queue using a static array stores elements in a contiguous block of memory of size n. Two integer indices are kept: front, which points to the first element, and rear, which points to the last element. The typical algorithm: int r open bracket n close bracket semicolon, int front equals -1 comma rear equals -1 semicolon void, in q open parenthesis, in x close parenthesis open brace, if rear equals n-1 open brace. Overflow condition print open quote q overflow backslash n close quote semicolon return semicolon close brace. If front equals -1 front equals 0 semicolon first element inserted r open bracket plus rear close bracket. Equals x semicolon place x at next free slot close brace int dq open parenthesis close parenthesis open brace. If front equals -1 or front greater than rear open brace. Underflow condition print open quote q underflow backslash and close quote semicolon return -1 semicolon sentinel value close brace in x equals r open bracket front plus close bracket semicolon return current front, then move forward if front greater than. Open brace front equals rear equals -1 semicolon close brace. Reset when q becomes empty return x semicolon close brace. Time analysis: both in q and dq perform a constant number of arithmetic and comparison operations, which is O of 1 time. Space analysis: the array occupies n cells, regardless of how many elements are actually stored, which is theta of n space. Overflow handling: when rear reaches n-1 the array is full, even if many earlier slots are empty because front has moved forward. The program must report overflow or resize the array, which defeats the static array model. Underflow handling: when front becomes greater than rear or both are -1, the queue is empty. Attempting to dequeue then signals underflow. The linear queue described above suffers from a wasted space problem. Imagine a parking lot with numbered spots 0 through 9. Cars enter from the entrance rear and leave from the exit front. After a few cars leave, spots 0 to 3 become empty, but a new car cannot use them because rear is already at 9. The lot looks half empty even though it is full from the program's point of view. This limitation forces us to either shift all elements forward after each dequeue, which is costly big O of n, or to reuse the empty slots. The latter idea leads to the circular queue, where the array is treated as a circle and indices wrap around to the beginning once they reach the end. This reuse eliminates the false overflow and keeps operations big O of 1 without moving data. Explanation: a circular queue also uses a fixed array of size s, but the front and rear indices are allowed to wrap around using modular arithmetic. The key formula is next index equals current index plus 1 modulo s. This means that after reaching the last slot s-1, the next position becomes 0 again. In queue of x algorithms, Step 1: compute next rear equals rear plus 1 modulo s. Step 2: if next rear equals front, then the queue is full, then report overflow. Step 3: if the queue is empty, front equals -1 set front to 0. Step 4: store x at array rear equals next rear. DQ algorithms. Step 1: if front equals -1, then underflow. Step 2: retrieve x equals array at front. Step 3: if front equals rear, only one element set front and rear to -1, queue becomes empty. Step 4: otherwise set front equals front plus 1 modulo s. Both operations perform a constant number of arithmetic operations, which is O of 1 time. The space used is exactly S cells and the queue can hold S-1 elements. One slot is kept empty to differentiate full from empty. No shifting of elements is required, so memory usage stays optimal. Complexity summary. In Q, theta of 1 time theta of 1 extra space. dq theta of 1 time theta of 1 extra space is full or is empty theta of 1. The circular approach therefore solves the linear Q's wasted space issue, while preserving the same asymptotic performance. Linear Q versus circular Q. Space utilization. For linear Q, waste slots left of front after several DQs may report overflow prematurely. For circular Q, all S slots are reusable. Only one slot is intentionally left empty, giving effective capacity S-1. Maximum useful elements. For linear Q at most S but often less due to false overflow. For circular Q, exactly S-1 or S if a separate size counter is kept. Complexity of operations. In Q/DQ, big O of 1, but may need costly shift if you try to reclaim space for linear Q. In Q/DQ, big O of 1 without shifting, using modular arithmetic for circular Q. Typical exam questions. Detect overflow when rear equals S-1, asked to show how many elements are lost after a series of operations. Write the wrap-around expression. Prove that rear equals front can represent both empty and full, so an extra condition or counter is required. When to prefer, very simple educational examples, or when the Q will never see many DQs for linear Q. Real-world buffers, for example producer-consumer, CPU scheduling, network packet queues, where elements are continuously added and removed for circular Q. Overall, the circular Q is the practical choice for any situation where the Q lives for a long time and elements flow in both directions. The linear version is useful for teaching basic concepts, or when the Q size is tiny and the overhead of modular arithmetic is considered unnecessary. A queue can also be built with a singly linked list. Each node holds a data value and a pointer to the next node. 2 pointers are maintained. Front points to the first node, the one to be dequeued. Rear points to the last node where new nodes are enqueued. In QNS, Step 1, allocate a new node with value x, and next equal to null dynamic memory allocation. Step 2, if the Q is empty front equals null set front equals rear equals new node. Step 3, otherwise set rear next equals new node, and then rear equals new node. DQ. Step 1, if front equals null underflow. Step 2, store temp equals front retrieve data equals temp data. Step 3, move front equals front next. Step 4, if front equals null after the move, also set rear equals null Q became empty. Step 5, free temp. Complexities both in Q and DQ involve only a few pointer updates, and a constant time memory allocation free O1 amortized. The linked list Q has unbounded capacity limited only by available heap memory, so there is no artificial overflow condition. However, each node carries extra overhead. The pointer and memory allocation can be slower than array indexing. In exam settings, students are often asked to draw the list after a sequence of operations, or to compare its space cost with array-based queues. Trace the queue after a series of enqueue/DQ steps. Write down the values of front, rear, and the contents of the array or list after each operation. Given a circular queue of size 5, start with an empty queue and perform in Q10, in Q20 DQ, in Q30, in Q40, in Q50. Show that after the last operation the array looks like 50-20, 30, 40 with front equals 2, rear equals 0. Detect overflow, underflow. For linear Q, overflow when rear equals size -1. Underflow when front equals -1 or front greater than rear. For circular Q, overflow when rear +1 modulo size equals front. Underflow when front equals -1. For linked list, overflow never occurs unless system runs out of memory. Prove O one time for all operations. Show that each operation uses a fixed number of arithmetic or pointer assignments, independent of the number of elements n. Write a recurrence. T in Q of n equals C, T dq of n equals C, where C is a constant implies T of n belongs to theta of 1. Convert a linear Q to a circular one. Replace the overflow test in the linear version with the circular condition. Replace index increments with index +1 modulo size. Calculate the number of elements currently stored. Circular queue, if rear greater than or equal to front, then count equals rear minus front plus 1. Else count equals size minus front plus rear plus 1. These kinds of questions test conceptual clarity, ability to manipulate indices, and understanding of edge cases. For a circular queue of size S, with array indices 0 to S-1, we keep one slot unused to distinguish empty from full. The maximum number of elements that can be stored is capacity equals S-1. If we maintain a size counter CNT, we can use all S slots, but the usual textbook formulation reserves one empty slot. Next index forward move is defined by next of I equals I plus 1 mod S. Previous index backward move is defined by previous of I equals I minus 1 plus S mod S add S to avoid negative results. Number of elements currently present can be computed from front and rear without a counter as follows. If front equals -1, the queue is empty and count equals 0. Else if rear is greater than or equal to front, count equals rear minus front plus 1. Otherwise, when wrapped around, count equals S minus front plus rear plus 1. Boundary conditions. Empty condition. Front equals -1 or front equals rear plus 1 when using a counter. Full condition. Rear plus 1 modulo S equals front. This condition arises because after a successful in queue we would make rear equal to front, which would be indistinguishable from the empty state, so we stop one step early. Proof of capacity. In the worst case, rear is just before front, that is rear equals front minus 2 plus S modulo S. The number of occupied slots is then S minus 1. No more elements can be added without breaking the full condition equation. These formulas are frequently asked in exams. Students are expected to write them, explain why one slot remains free, and demonstrate how they prevent ambiguity between full and empty states.